Hi, good evening everyone. Am I audible?
Yes, sir.
And is my screen visible now?
Yes, sir.
Should we wait for some time? Maybe some other people may join like 2 to 5 minutes. Is it fine?
Yes, sir.
Hi, good evening everyone. Is my voice audible? Am I audible?
Yes.
Okay, let us start today's problem solving session. Just a minute. Hi, good evening everyone. I am Adnan Farooq Khan and I am a PhD scholar at IIT Delhi, and I'll be doing today's problem solving session for the course NPTEL course Advanced Power Electronics and Control, which is being taught by Professor Avik Bhattacharya. I'll be conducting this problem solving session. I'll be conducting this problem solving. Just a minute, someone wants to join the meeting. I'll be covering the problems relating to the topics that were taught to you in this week by the respected professor. And this problem won't be related to the assignment that has been given to you in this week. These problems will be mainly pertaining to the topics that have been covered in this week, and won't be the problems that have been given to you as an assignment. There are Sorry to interrupt. Like, they are asking to let them join, and I have to add them. Just sorry for this. Like, they were asking, so that I had to add them. So once again, I am Adnan Farooq Khan, and I am a PhD scholar at IIT Delhi, and I'll be doing this problem solving session for the NPTEL course Advanced Power Electronics and Control. This is being taught by Professor Avik Bhattacharya. In this session, I'll be let me go into the slideshow mode. In this session, I'll be covering the topic. I'll be doing the problems on the topics that have been already been covered in this week by the respective professor. However, these questions and or problems won't be the assignment that has been given to you in this week. I'll be doing this problem solving session on every Tuesday from 7 to 9, like this slot every Tuesday. We can gradually be doing these assignments only after their submission date is completed. Like, if the submission date of the assignment is in this week, like if there is a problem solving, there is a problem solving, there is a problem solving session. So, just a minute. I'll be doing this problems. There are two other slots for the problem solving sessions. One is being conducted by my other fellow on Monday from 6 to 8, and other is being assigned right now, I think, conducted from 6 to 8 on Tuesday. During these problem solving, first I'll be briefly going through the contents that have been taught to you in this week. I'll briefly summarize them so that you can brush up the concepts that have been to brush up the concepts that have been taught to you by the professor in this coming week, which can help you in like doing the assignments and other things, and also the problem solving. This week's summary was mainly the introduction to the power electronics. Was mainly introduction to the power electronics, the applications of the power electronics. What are the advantages? Why we are studying the power electronics, and what are its applications, advantages, and what are the like basic thing for the power electronics, like the basic concept of the switches, how the like different converters will work, what are the different working operations for the different converters, and what are the different switches available to us that can be used, and what are their features, and lastly what has been taught, like the professor taught about the device physics of these switches has been taught. I will briefly summarize what has been already taught in this week, and then we will move forward with the questions that need to be solved. Like firstly, coming to the introduction, what we want to know is why the power electronics. As we can know, like the electricity available to us is in the form of AC, and it has a like a fixed voltage and a frequency. Let us say a single phase of like a 230 volts, or a three-phase system with a line-to-line voltage of like a 415 volts. However, if we want to change these voltage levels, like we can do it from by the utilization of by using a transformer, which can transform a voltage level from one voltage level to other. Let us say there is a transformer with 1:n voltage ratio, and let us say we are having an input of a 10 volts, let us say, and are at the output we will be getting it with a transformation of n into that amount of the voltage. However, with this transformer, we will be able to get these different voltage levels, but we won't be able to like change the frequency of these things. Also, there are certain utilities. There are certain utilities, certain equipments that we use that use the DC, and there is no equipment. There is not a transformer that will convert from AC, that by which we can convert AC to a DC. This was the other motive behind that. Besides this, also, as we know, there is no DC to transformer. As such, we won't be able to like have a different voltage, DC voltage levels, which are required for different appliances or equipments that we use in the day-to-day lives. For that purpose, like power electronics is being used. Besides this, we don't only want this thing like to have a to have a conversion of a voltage from one level to other, or get a variable have a variable frequencies which is being utilized for different applications, like let us say in the variable frequency drives, where the speed of the motor can be changed with the frequency. Also, besides this, having this conversation, what else other things we want is having a higher efficiency as well. This can be achieved by higher efficiency. We only not only mean this. We not only mean this like just a minute, sorry. we also want to have a higher conversion, higher efficient conversion, as we need the energy conserved is we want to conserve the energy. We want to save the energy. Let us say if we are having an efficiency system there are, and we are able to reduce the loss, we are able to reduce the loss somehow. We can say like we have conserved the energy. Also besides this, we also want a flexibility. As I was earlier telling you, like we want to have the different voltage levels and frequencies to drive the different different voltage levels for different equipments, appliances, and for different frequency for our variable frequency drives or motors. This power electronic converters provide us with this ability. Besides this, we also want, with the use of this power electronics, we want to achieve the high power density. What do you mean by high power density? As we are able, as we know, we want to achieve the higher efficiency conversion. By this high efficiency conversion, we not only want, like we are able to reduce the losses. This means when we are able to reduce the losses, this means that, let us say I'll tell you in this way, like if there is a system and the loss, and there is some amount of loss happening in the system, this loss will dissipate, will be dissipated in the form of a heat, and we need to dissipate this amount of a heat. Let us say a lot of the loss is happening in the system, so we need to dissipate this amount of the heat. We need to have the proper equipments like the fans, or for a high power converters, we need to have the proper cooling system to dissipate this amount of the heat. However, if we are able to have a high efficiency conversion, that means like we are able to reduce the losses. We are able to reduce the losses as such. We, in another way, we can say like we have a reduced requirement of these heat sinks and other fans and other things. Someone has like there are where was I, like when we are able to have a high efficiency, we are able to reduce the losses. As such, we don't have to dissipate that amount of heat. As such, we will be able to reduce our thermal components like heat sinks, fans, and other cooling things, which can in turn achieve by which we can in turn achieve the high power density. Like we are able to reduce the size of the converter. What was the thought in introduction? Like, what are the major applications of this power electronics? Where can we find its application in our day-to-day lives? As we can see, like the current trend is like the renewable energy source. Like we are having solar, wind energy, like all these renewables. But we can see like this solar energy is formed in the form of a DC energy, and we want to have this, we want to convert this DC energy to DC to AC. For that we need a converter, DC to AC converter. As such, we are able to integrate this renewable to our AC grids through the form of a power electronics. Let us say a converter which will be like a DC to AC converters. Also there will be a there will be some fluctuation between the different power levels or power levels. We should be able to adapt to them, or we should be able to work properly with these voltages. Besides this, other application is like variable frequency motor drives, like we find in the motors, like the motor used in the vehicles. As we can see, like the speed of the motor, by varying the frequency, we will be able to vary the speed of these motors and machines. Currently we are seeing the electric vehicles. Electric vehicles is a hot topic right now. Right now, where we are having a DC, bank in the form of a battery, which is used which is used to drive these motors, used to drive. As such, we need to have form of a converter which can transform this DC to AC. Besides this, also in these electric vehicles there are like these battery banks. We need to charge them. As such, we need to have an AC to DC power conversion by which we will be able to charge these batteries. These batteries. Some other applications that you can find in your day-to-day lives is like a UPS, uninterrupted power supply, which will be available, I think, in all of our homes. It also has a DC bank, which is like a sort of a battery. Then there is an inverter stage which converts this DC to AC, on which our various equipments like fans and other things run. Besides this, we will be having some other components like we'll be needing different equipments which can have different voltage levels. Like we have a 1 DC and we want different voltage levels for different DC voltage levels for different equipments. As such, we'll be needing DC-DC converters which can make the proper voltage transformation so that we can drive these equipments. Besides this, also we can have like AC to DC transformation. Also, the other thing that has been possible with power electronics is the power transmission with the high voltage DC. As we know, like the DC transformers weren't available aren't available to us, but with the help of these power electronic converters like solid state transforms and these, we are able to convert these high voltage ACs to high voltage DCs, and then we are able to transmit then we are able to do a high voltage DC transmission. Besides this, the other factor is like a power quality factor. What do you mean by power quality factor? Like we want to have a unity power factor in our transmission. Like whatever the power that will be what will be taking from the grid, we want to have as close as to the unity, so that the apparent power will be equal to the real power. If our quality factor is deteriorated, like that means like we'll be driving the more apparent power from the source. We'll be driving the more we will be trying to have more apparent power from the source. Source which can lead to the more amount of the which can, in terms of the current, let us say it is drawing more amount of a power. That means it is drawing more amount of the current, which can increase the losses in our system. One thing is that like that power quality is being deteriorated due by the use of these converters and power electronics. But also these power electronic converters provide the solution with that. Like we are able to have the unity power factor and improve the power quality. Which will be doing in the detail, like further in your course, which will be taught to you in detail further in the course. Coming to the basic concept of the power electronics, like is the basic concept, like is a basic building block, I can say, is a switch. Let us say here in this example, let us say, in this example, what we want to have is from a source of 100 volt, we want to add the output across the 10 volt of a resistor. We want to have a 50 volts. Traditionally, how we will do is we will be using this voltage dividers. We will be having some other resistance of 10 ohms connected in series with this resistance, and we apply this, and the voltage across these resistors will be equally divided, and we'll be having like the 50 volt across our load. This will be the traditional way how we will do it, but this is not a very efficient way of doing it. As you can see, like we are able to get the 50 volts at the output, but 50 volts at the output, as you can see, the whole current drawn is the same through both of the resistors, and the 50% amount of the energy is dissipated in the internal resistor or other resistance. As such, we'll be only having like of 50% efficiency. That means that means this system is not that much of a efficient. Similarly, if we want, let us say from 100 volts we want only 30 volts to be at the output, we can do that by appropriately conducting that inductance, so that we can have a 30 volts at the output. But by doing that, we'll be having only the 30% of the efficiency, and 70% of power will be lost in the other resistance. Like this solution is the quite lossy, and this is not a proper solution which we'll be looking for, as we don't want to have. We want to have a high efficient system by which we will be able to minimize as much of the loss as possible. So other thing is, the other way of doing this is by the utilization of a switch. Let us say like we still want to have the 50 volts at the output. Is there some way we can have that 50 volts by the use of a switch? What we will be doing is, for the time being, we won't be talking about like what kind of a switch this might be. It is like a switch, maybe let us say a mechanical switch that will be closed for some period of time and will be open for a certain period of a time. Now what we want, our objective is like to have a 50 volts at the output. So what I will do is like I'll be closing this switch for like t/2 of the time, like 50% of the duration. So I'll be getting the 100 volts at the output for this amount of the time. Then I'll be turning off this switch for the half amount of the time, as is shown by this waveform. Like we'll be getting the 100 volts for the 50% of the duration, and 0 volts for 50% of the duration. If we calculate the average of this voltage, like it will be 50 volts that will be across the output. Also, as this switch is like a short or a conducting wire that can be that makes or breaks the circuit, and there is no lossy component in this switch. Like we are considering it as an ideal switch. As such, there is there is no loss happening here. As such, we'll be able to have a good efficiency, of about 90% in the system, and we'll be able to have that 50 volts at the output. Similarly, if we want to like now, instead of a 50 volt, we want to have like a 30 volts at the output. What we will do, we will turn on the switch for that certain amount of, like for the t/3 amount of the time, like we'll be getting a 33% average at the output. Like we can have the different amounts of the voltage. We can do the buck operation, like we want to have different voltage levels. By appropriately switching, we can achieve whatever we want to have. That is what we were talking about, like having that control. What we want to achieve, like we can have different levels of the voltage achieved at the output as per our need. As we now know, like this switching mechanism will be of very high frequency. Like we'll be repetitively switching this switch on and off, on and off, on and off. As you can see, because of that, with this average will be average DC component that will be across the load, will be getting a high frequency component over it, and to eliminate this high frequency component will be we have to use some small filters which will filter out these switching frequency components. Now coming to the switches, like we had previously discussing, like we can achieve different power different voltage transformation with the utilization of a switch. Now what we want to know is, how should our ideal switch look like? what should be its properties, or what should be its main features. Considering the ideal switch, what it should do, like it can have like two stages, like we can turn it on, like we can turn it off. But when we turn it on, it should be able, like there should be no voltage drop across it. When we turn on the switch, an ideal switch should have no voltage drop across it. That means it shouldn't have a if there is no voltage drop and the current will flow through, there will be no loss across this switch. However, in the practical day-to-day in our practical, this is not possible. There is some certain amount of voltage drop which will cause some certain amount of loss in that switch. And switch should be possible, like it should be able to carry the high amount of the current. Like the one point our switch should be able to do is, like in the on state, it should be able to carry high amount of the current. Now in the off stage, coming to the off stage, in the off stage, when we open the switch, the switch should be able to block the amount of the voltage that is being applied across it. Like it shouldn't get damaged with the amount of voltage that is applied across the switch. It should have that withstanding high voltage capability, or the voltage that is being applied across it. Like these two factors like are the main factors like we look for while like choosing a switch in a circuit. What is the amount we look for? What is the amount of the voltage that will come across it? Should this like a switch be able to withstand that amount of the voltage, or should this voltage this switch be able to carry this amount of amount of current through it, so that it won't get damaged. And beside, and when we choose this switch, we always like keep a margin of the safety, margin of safety. Let us say like we want a switch in our circuitry that is of the high let us say of the 100 volts, like it has to block 100 volts. Like we choose a switch like which has certain margin, like 1.2 or 1.5 times, like so that if at a certain moment of time, there is a uh, increase in the voltage, like it should be able to bear that amount of the voltage. The other feature like switch should have, that it should have an instantaneous turn on and turn off. What we mean by the instantaneous turn on and turn off, like when the switch will turn off, when the switch will turn on, like it should be carrying the whole amount of the current, and or which it should be turned off, like voltage when it should turn on, like voltage should go from the voltage blocking to zero abruptly. But this doesn't happen in practically this doesn't happen, and there is some lag between when the switch is turned on and switch is turned off. As you can see, when the voltage, let us say a switch is blocking certain amount of a voltage. Now when the switch is turned and the current through it is zero, and when the switch is turned off, switch is turned on, like this voltage has come to the zero and this current has to rise. And if you can see, like in this transient transient portion, like as soon as the this voltage is rising and current is decreasing, there is certain amount of time where these both voltage and the currents are there is certain amount of this voltage and the current. This will cause certain loss in the switches. Also keeping that in mind, and the switching that we are doing at high frequency switching will result in the certain amount of the switching losses at these instant of times in these switches. Now coming to the different switches that are available, like power electronic switches. Like before talking about these power electronic switches, like we can have a switch like a metallic switch between, that is having a between like two metal contacts, that when they come in contact with one another, they will start conducting, and when we break the contact and break the contact and the conduction will stop. However, these switches are very slow, and in our like power electronics, we want to switch at very high frequency. So Coming to the like basic concept, like what are the various switches that are available to us. Like the basic switch that is like is a diode. As you can see, like this is a diode. As I was earlier talking about, like we define the characteristics of any switch is the way it will conduct the current. Like the switch has to conduct the current and block the voltage. And if we can see, when we apply the positive voltage, that means like this, as you might be knowing, a diode consists of a PN junction diode, can consist of an anode and a cathode. When this diode is when this diode is when this diode is forward biased, that means that anode is at a positive potential and the cathode is at a negative potential. The diode starts to conduct. That means the diode will conduct the positive current, as can be seen in this graph. Like this is the positive direction. Like diode is able to conduct the positive current. However, when the now we have to see what polarity of the voltage it will block. Like this is not able to block this positive voltage. However, if we give a negative voltage, like cathode will be positive and anode will be negative, the diode will stop conducting. Like the diode will be reverse biased, or the diode will be reversed. As such, you can see like the diode is able to block this negative voltage. With these characteristics, we'll be able to say that the diode is having a one quadrant operation. Like it is able to have a single quadrant operation, and that is in the second quadrant. Also, when the current is negative, like the negative current isn't able to flow through the diode, we can say like the diode is having a single quadrant operation. Coming to the other category of the switch is the SCR. Here what we have is like I was talking about, is diode is a PN junction, but the is a two-terminal device with an anode and a cathode. Talking about the SCR or a thyristor is a three-terminal device where we have an anode, cathode, and there is an additional terminal, as where I am moving my mouse. As you can see my pointer, this is the gate. This is the gate terminal. And with respect to the diode, like diode was having a one quadrant operation. With respect to the diode, this SCR will conduct only when we will be applying a certain gate to it. Like if we give the positive voltage to this SCR, it is able to block this positive voltage. It is able to block this positive voltage until a gate is given. As such, as such we can say like the SCR is able to block this voltage. Like we have to keep this in mind. Like while doing these characteristics, two things need to be kept in mind. This switch has to block the voltage and has to conduct the current. However, when we give the gate to it, like if you are giving the positive, it will start conducting the positive current, like that is being shown here. This SCR is like control turn on device. However, we can't control its turn off. The SCR turns off when there's a negative voltage applied to it. That is being shown here. Like it is able to block the negative voltage, or the negative current flows through it. Like it is not able, if there is like a negative current, if there is an SCR in a circuitry and a negative current is flowing in the path of the SCR, it will act as a closed switch for that. It won't allow that negative current to flow through it. As such, we can say this SCR is having a two quadrant operation, like in the first quadrant and the second quadrant. Moving forward, there is a other class of switches, like where we can say like is a bipolar junction transition BJT and a IGBT, isolated gate bipolar transition, and a MOSFET. As we can see, is BJT. It is able to, like we are having a we are having a collector, emitter, and the base terminals here. Like there is a 3-terminal device with the collector, emitter, and the base. And when this in the SCR we were giving the gate to it. Just a minute. Here we provide this base current to the BJT, and it starts conducting. Similar to that, it is able to block the voltages. It is able to block the voltage till this base current is giving, and it starts conducting the positive current. And if this base is withdrawn, base current is withdrawn, like it will stop conducting. And as we can see, like it is not able to block this negative voltage. Also it won't allow this negative current to flow through it. Coming to this other part is like a IGBT. Here as we can see, like this gate is isolated from it has a similar characteristics to that of the BJT, where when we give the positive voltage, it is able to block till we provide some gate to it. As soon as this gate voltage is we give this gate voltage to it, like it starts conducting. It's able to conduct this positive voltage. However, it's not able to conduct in the reverse direction, as it will have the one quadrant operation, and that too in the first quadrant. Coming to the other switch is the like what we call is a MOSFET. Similar to the IGBT, it will block it will block positive voltage till the gate is given, and it starts conducting. After that, it is able to have this positive current. It is able to have current. However, in this MOSFET there is a anti-parallel diode in this well, which is able to conduct this negative current as well. As such, it is able to conduct this negative current. Thus we can say this MOSFET is having a 2-quadrant operation, and it will operate in the first and the fourth quadrant. This was a little bit summary about these switches. Now what was lastly taught about is the device physics, about the general concepts. I won't be going into the detail, like briefly summarize what is behind the physics behind these switches. As we know, like all the switches that have been discussed up till now, all these comprises of these PN junctions. Like every switch comprises of these PN junctions. And first I'll be talking about how this PN junction is formed. Like if we are having a silicon element, like which is also known as an intrinsic semiconductor, the pure silicon, when it is like doped, when an impurity is added to it, this silicon belongs to the fourth group of the elements, have the 4 electrons. Like when it is doped with the n-type, and when it is doped with a pentavalent impurity, that means which has the of the group 5 elements, we call it an n-type semiconductor. Because as we can see, like when we doped it with the pentavalent impurity, like 4 of the electrons are able to make the bonds with this silicon, and what is left behind is the 1 electron. Like electron is having a negative charge, in a sense you can say, like as such we will be calling it as a n-type semiconductor. And these doping can be of, like it can be lightly doped or heavily doped, and depending on that we call it like a n minus for like lightly doped silicon, and n plus for when which is heavily doped. Similar to that, and if we have a if we add trivalent impurity to this silicon semiconductor, three of like which correspond to the third group of elements like boron, like three of three of these electrons will be able to form the covalent bonds with this semiconductor. However, there will be a one hole left, and this hole can be considered of like an electron with a positive charge. Like there is a hole, it is a positive charge as such, which help us in the conduction. As such, it's known as the p-type semiconductor, because there is a positive charge. There is not a positive, like the carriers in these are positively charged, and in the n-type there is a negatively charged carriers which carry this amount of the current. Coming when we are having a p-type semiconductor and n-type semiconductor together, they form a p-n junction. I won't go into the details of the like the physics behind it. When the p-n junction, it will have a certain, like I was telling you, like let us take a diode which form of a p-n junction. It has a certain breakdown voltage, amount of the breakdown voltage, and this breakdown voltage will be a function of the doping level. How much are we adding, how much impurity we are adding to this semiconductor. If our semiconductor is lightly doped, that means we haven't added that much amount of the impurities into the semiconductor. Our switch or electronic device will have the high breakdown voltage. But what we can say is the downside of this is, like these low doping switches will have high resistivity. That means, like the switches, let us say there is a switch rated for like a 100 and 200 volt. Like the switch for the 100 volt, for the 100 volt will have small less on state. When when it will be conducting the current, it will have the small amount, like the less resistance across, and it will have the less drop as compared to the 200 volt switch, which will be having the more resistance, internal resistance. And coming out to be these, like we are having different devices, as we had discussed earlier, like MOSFETs, diodes, like transistors, IGBT, BTS. These are when like I was telling you, when we add impurity to this silicon, like n-type or a p-type, when the n-type impurity is added, like we can say the majority carriers are the whole here electrons, and with the p-type we say like the majority carriers are the holes. And in the n-type we say the minority carriers, when we are having the minority carriers are the holes and majority carriers. There is a p-n junction, like we are having like a BJT NPN, we say that the majority carriers are the electrons, the minority carriers are the holes. As we can see, like these MOSFETs and Schottky diodes, these are the device like majority carrier devices. The conduction through it is possible with the majority carriers, be it like n-type. When we say n-type, then we can say like the current is conducted by the electrons, mostly the electrons. Similarly, these diodes, thyristor, BJT, IGBT, these are the minority carrier device, and whatever the current that will be flowing will flow through these switches. It will be all because of these minority carriers. These are the concept between this p-n junction diode. What we do is conductivity modulation, like to decrease on-state resistance. Like I was talking about the on-state, some devices will have on-state, like with low doping, the on-state resistance will be large. What we want is like to have a reduced on-state resistance, so that the drop will be very less, and there is not much dissipation across this. There is not much conduction loss across this device. And to have that, what is done is like a conductivity modulation. There is lightly doped that I'll come in that will be covering in the question, some questions. When we are talking about the power diodes, between the P and N there is one other portion that is like lightly doped. We call that a drift region, and we add a lightly doped region, and this minority carriers are injected into this lightly doped region, which will reduce the on-state resistance. However, this had a disadvantage of like these minority carrier device has a disadvantage of a reduced switching speed. Since like we have added minority carriers into slightly doped region, when we are like reverse biasing or trying to turn off this device, what has to happen is to like the reverse recovery and reverse recovery time will be more like to push these minority carriers back, which will take sufficient amount of the time, which will take certain amount of the time. As such, like these devices are not utilized for high switching operations, because there what we require is like less reverse recovery and all. So what can be summarized here is like what we saw is this diode. What it have is it is having an uncontrolled turn off, that this will help us in problem solving and help you with this with these assignments. Is like what we saw is like a diode. It was able to have uncontrolled, it is like an uncontrolled device which is having a uncontrolled turn on as well as the turn off. As we saw, when the positive voltage is applied across this diode starts conducting, and whenever the negative voltage applies across, or the current is negative, it stops conducting. That means we don't have any control over its conduction. It starts conducting on its own as per the circuit how the voltage will be applied across it. Then we are having other device like I talked about is thyristor SCR, which is able to have control turn on. We are able to turn it on when we give a certain gate to it, and it starts conducting. However, we are not able to turn it off, and there is no control over the turn of this SCR. There are other devices where we can control both the turn on and turn off. These are GTO, BJT, IGBT, and MOSFETs that I already briefly told about that as well. The devices that are able to have this bipolar voltage standing capability, like that they are able to block both positive as well as the negative voltage, are like these SCR and GTO. That will be explained in this some exam like problem, but there is a question about this, and I'll tell you about that. And these the BJTs, IGBTs, and MOSFETs, these are the unipolar devices, and they are able to only block they are only able to block the positive voltage up to a certain amount when the gate is given. And then also the device that is able to have the bidirectional current operation is like a triac. And this was like the summary that what had been taught to you in this week by sir. Now applying keeping these things in mind, like there are certain problems that will help you in understanding these concepts, and which will certainly help you in doing your assignments. And we'll be doing some problems here, and shall we start doing the problems? So as you can see, like the first problem is everyone is able to see the screen.
Yes, sir.
As you can see, the first problem is like MOSFET is which type of a device. Like there are certain these given options given, like it's a current controlled voltage device, voltage controlled voltage device, voltage controlled current device. And before like going to the solution of it, like I want you people to try like what do you think can be the correct option. You can like text in this in message, left the message so that I can see like you try it at least. What do you think? What is the right option? Anyone? One of you has sent it like it's a current controlled voltage device, like B option. Anyone else? Okay, let us. Uh, mm, Other option is like D, voltage controlled current device. Let us come to it. Let us see what is happening in the MOSFET. As we can see, like the MOSFET, we are having like a three terminals like drain, gate, and source. As you can see, like the gate is isolated. Gate is isolated. We called MOSFET as the isolated gate, and like no amount of the current can flow. So the amount of the current that will flow through like a drain source is a function of the VGS voltage that will be giving between the gate and the source. Is a function of that. That means like coming to the first part, like it will conduct only when we will be giving certain amount of the voltage between this gate source. As such, it is a voltage control device. Like it means like we are able to turn it on when we get a certain pulse. If we give certain gate source voltage, it will start conducting, start and the drain current begins to flow after the threshold in this VGS voltage is crossed. Like when we give a certain amount, then there is a certain threshold. If if you don't give the voltage up to that threshold, it will start conducting. When the voltage goes beyond this threshold, it starts conducting. And when this gate source voltage becomes negative, and we can say the MOSFET is turned off. Like as such, coming to this, as you can see to this like BJT, you can have seen like this BJT. This is a current controlled device as compared to the MOSFET. Like base is connected to this base is connected. It is not isolated, and the collector current is a function of like of the base current. Like you have seen IC is beta times of IC that you'll study in this. That here this means this is a current controlled current device. As such, like we will be coming to this option. As you see that this MOSFET is like a voltage controlled current device. Voltage, like option D is correct. Like this MOSFET is able to conduct the current after this VGS voltage is given. Now the next problem is, as compared to this PN junction diodes, the Schottky diodes have low operating frequency, low reverse leakage current, high operating frequency, low reverse leakage current, medium operating frequency and low reverse leakage current, high operating frequency and high reverse leakage current. Anyone?
High operating frequency.
Like you can type it, like you can type. Can you switch off your mic, please?
Yeah, it's like high operating frequency with high reverse leakage current.
High operating frequency, high reverse leakage current. Okay, can you turn it off? So firstly, there are like multiple options are coming. Someone is saying B, some is saying D. Now let us go into it and see what's happening in the Schottky diode. Here we can first I'll be talking about this p-n junction diode. Like I told you, like this was a brief. There will come in certain sections of these problems where I will be discussing in detail the operation. As you can see, this is a power diode. Here we are having a P connected to the anode and N connected to the cathode, and there is a region N minus, like a lightly doped region, is called the drift region. As when this when this diode is forward biased and it starts conducting, and when it starts conducting, like in the diode, as I already told, like the conduction is through minority carriers, and these minority carriers like are from P to N. And when we want to like switch off this diode, let us say this is the ID is the amount of the current, certain amount of the current that is flowing through the diode. Now we want to switch it off. We want to turn off the diode. As soon as like we begin to turn off this diode, like the current starts to decrease. The current has decreased, like the voltage has not yet been to zero. There is a certain amount of voltage still. Like as soon as this current reaches to zero, there is still certain amount of minority carrier charges which are to be eliminated, like so as to stop the conduction process. That means we give this VD voltage, like reverse recovery voltage, because of these minority carriers. There is a reverse recovery current flowing there is a reverse recovery current flowing for a certain amount of the time, and this reverse recovery is not good for high frequency operation. The more the reverse recovery, like we won't be able to have a higher switching frequency operation, because there will be certain losses in this, because there it is still conducting some current, and there is still some voltage, and there will be certain loss across the diode. And this is with regards to the power junction diode. Like it won't be able to have the high frequency operation, because the like reverse recovery is taking a lot of the time. This reverse recovery, like in this reverse recovery, like there is a reduction of these minority carrier charges that are there, and till it becomes like a this becomes all the minority carriers are gone back, and this current is becomes zero. Now coming to this Schottky diode, what differentiates it from the p-n junction diode is, like instead of a p-type we are having a metal that has been in contact with the N, that is in contact with this N semiconductor. And what we know, like this in the Schottky diode, the it's a majority carrier, like in the metal the current through this Schottky diode is carried through the majority carrier electrons, which are the electrons, like when there is a when this is turned off, there is no like that drift region in between this, so there is no reverse recovery there, where there are the minority carrier charges which are to go back and do the recombination. As such, with this Schottky diode, we will be able to have higher switching frequency, because the reverse recovery is very less. However, as we can see, this PN junction diode, this depletion region that will be formed due to this N minus will be very large, which won't allow any which won't allow that much amount of the leakage current. When you go into the physics of it, like a potential barrier is developed, and it is reverse biased, and this won't allow the leakage current, that much amount of the leakage current to flow through it. However, in this Schottky diode, there is large there is like a depletion region is not, when this is reverse bias, the depletion region is not that big and is very small. As such, when it is reverse biased, high reverse, there is a chance like a high reverse leakage current will flow through this Schottky diode. As such, like these Schottky diodes are rated for like a small amount of the voltages, because like of this small depletion region, they are not able to withstand that amount of this voltage. As the correct answer is high operating frequency and high reverse leakage current. That because of the small reverse recovery time, it is we are able to operate it at higher frequency. However, due to the small small depletion region, we are not because of the small depletion, there will be high reverse leakage current flowing through this Schottky diode when reverse biased. Coming up to the third problem, like one of the difference between diode and the triac is like different options are given, like diode has control turn on and triac has a control turn on. Diode has a control turn off and triac has a control turn on. Diode needs gate pulses to turn on and triac doesn't need. Diode has a unidirectional current flow and triac has bidirectional current flow. Can anyone guess what is the current? Like one is telling like D, diode has unidirectional current flow as, and triac has bidirectional current flow. Let us go into it like C. As we had already discussed, like a diode is like a PN junction where P is connected. When P is connected to the positive terminal and N is connected to the negative terminal, we can say like this is the forward bias. And when the N is connected to the positive terminal and P is to the negative terminal, we can say the diode is reverse bias. Like the diode is similar PN junction. It's someone's mic is on. Can someone's mic is on? Can you close, please? So as we have already discussed, and like diode is able to conduct, but that is when there is a positive voltage across it, and it will not conduct when there is a negative voltage or negative current flowing through it. However, we don't have any control, like we want to turn on diode at a certain instant of a time, like we want to impose our will on the conduction of our diode, like it should conduct in this period of time. We cannot do that. Like it will all be determined what voltage and the current is in the circuitry. If the positive voltage is applied across this diode, it will start conducting as such, and the current will flow from anode to cathode. It will conduct the current in only one direction. Coming out will be the triac. Like triac is like we can consider is like an SCR, which are conducted in the anti-parallel direction. However, they are having a common gate. Like we saw with the SCR, like SCR was able to block positive as well as a negative voltage. We had a control on its turn on and turn off. However, it was only able to conduct the positive current. But with the addition of this anti-parallel either diode that has been connected in the NT parallel, it is able to conduct the current in the reverse direction as well, because at that moment of time this SCR, the second SCR will conduct. As such, the current can flow from T1 to T2 as well as from T terminal, T1 terminal to T2 terminal, also from T2 to T1. Like it can conduct in both the directions, and it has a control turn on because of this gate, and it will turn on only when the certain gate is applied across it. As such, coming out to be this like the option everyone has had like guessed correctly. Like it has unidirectional, diode has a unidirectional current flow, however the triac has a bidirectional current flow. And before moving forward, can we can take a 5-minute break, and we'll be joining like it is like 8:11. We can join around 8:15 or 8:16. Is that fine? Yeah. So we'll be joining in like 5 minutes. Vanishri ji has raised his hand. Is there something she wants to ask? Like if there is some question, like you can ask. Shall we start? Everyone is back now? Like Shiva is asking like how what will be the exam pattern. Like we don't know about the exam pattern, like that will be decided by the NPTEL. What we are like doing is like do this problem solving and help you in solving the problem and understanding the concepts. Like if you face any difficulty, you can tell, and all that will be decided by the NPTEL people, and we are not aware of that, like what will be there in the exams, or it will be certainly decided by the concerned faculty who is teaching this course. However, if you have uh, any difficulty in understanding anything, like you can ask. Hope you got the answer. Like coming to the fourth question. Coming to the fourth question, like this is AC motor behaves like which type of filter? Like there are four options, like low pass filter, high pass filter, band pass filter, or none of these. Anyone? Yeah, someone has written like A. Any other? So we can see, let us see how does a typical three-phase AC motor look like. Like briefly what I can say, like a motor comprises of like two parts. There is a stator part and there is a rotor part, and this stator part is responsible for generating the magnetic field which causes the rotor to rotate. And in the stator, this winding is distributed over this whole stator, and the current is flown through this stator, and which causes the magnetic field to which causes to develop the magnetic field. Since the rotor can also, like an induction motor can typically have, can have the coils, or can have the bars, squirrel cage, or one rotor type, which we will learn in the machines course if someone has taken up that course. So like current will be flowing through this stator. However, this stator it will comprise of this whatever I'll say, like of a coils which will have a huge inductance. As we can say, like for a three phase, like AA is one phase, B dash, and C dash are the three phases of these stator windings. And there is a inductance in each winding, like A has its own inductance, B dash, and C dash inductor. Now let us say, like let us take a one phase, like IA phase. Let us see about it. Let us say there is a certain amount, there is an inductance L in this winding, and we know that the impedance that is being offered by this inductance is omega L, or 2 pi FL. And whenever this current, any amount of the current that will flow through this inductor, let us say it has this flow through the inductor, it will have like low frequency components as well as the higher frequency components. So as we know, like this impedance in This impedance of this inductor is dependent on omega, like just a minute. Has its own inductance which is dependent on the frequency. As you know that IA is dependent on like VA by omega L. This means like when the frequency for the lower frequency components like this omega L will be very small. As such, like we can say like in a way for the lower frequency components it will for the lower frequency L inductance will offer a low impedance to the lower frequency components. That means the I value will be very high for these lower frequency components. However, for the higher frequency components, like this L will offer a very high impedance, as the impedance of an offered by the inductance is directly proportional to the frequency. This means like with the high frequency, the value of this the higher frequency component of the IA will be very small, or like you can say these higher frequency components are attenuated like this inductor doesn't allow it to pass. This means like the inductance is able inductance allow the low frequency components to pass and like uh, uh, attenuate the higher frequency component. As such, like we can say from this, let us say we are having an AC supply where we want to drive this three-phase motor, AC motor. However, we want to control it. Like I already told you that the speed is dependent on the frequency. If you can say for example, this 120 f by p, the synchronous speed, and it is directly proportional to the frequency. Since the poles on a machine will be constant. So when we are having an AC voltage supply, it is having a constant frequency. We want to have this constant amplitude and constant frequency AC voltage. We want to have we want to have sort of a voltage which will be having which will be of which we will be able to like control the amplitude as well as the frequency. As I had already told, like we'll be having then AC to DC first, then DC to three-phase AC. Here, as you can see, like earlier at the beginning, I had told about the concept of like switching. Is my voice audible? Like someone is messaging, I'm not audible. Can others confirm? I'm audible to other people. Like, can you please check the microphone of your laptop or whatever device you are using? So moving forward, like first we'll be doing like AC to DC, and then we'll be doing DC to AC, and then we'll be properly switching this DC to have a certain amount of the frequency. As early start of the beginning, I told you like we can have a different amount of voltages, different amount of the voltage applied by properly changing the switching patterns. Like here, the switching pattern is like first it is very small, then the time for which the switching is applied, like this is a sinusoidal PWM that is being done in the inverter stage, which we use subsequently learn here, telling you in terms of the voltage applied. If you can see, at the beginning, small amount of voltage is applied, the average of which will be very low. Gradually, then the pulse widths are increasing, which you can say in a way the instantaneous higher average value is attained. Then it goes up to the peak, and then it further reduces, and in a similar way it goes in the negative direction as well. Then we can say this voltage waveform comprises of a fundamental sinusoid, which has with the high frequency components, which are due to the switching. Due to the low filter property of this induction motor, only this fundamental low frequency component will be passed, and these high frequency components will be attenuated or eliminated. As such, the answer is a low pass filter. Coming to the fifth question, a variable coming to the fifth question, variable frequency drive a variable frequency drive is used to, first part is control AC motor speed and torque by varying motor input voltage. B is control AC motor speed and torque by varying motor input frequency and voltage. C is control motor input frequency and voltage by varying motor speed and torque. D is control motor current and voltage by varying motor speed and motor torque. Any one of you? Most of you are telling me is a B option, control AC motor speed and torque by varying motor input frequency and voltage. Coming to the first, the variable frequency drive. What is a variable frequency drive? I was earlier telling you about this in this three-phase induction motor, about as in the low filtering property of it. Let us say a variable frequency. Let us say we are having a three-phase. We are having an AC motor, or we want to change its speed. We know that the parameter by which we can change its speed is frequency. If we are able to change the frequency, we'll be able to change the speed of this motor. However, with this, with the change in the frequency, the flux will also change. We don't want our flux to get that high, so that our motor will get saturated, motor will get saturated, which will cause a tremendous amount of which will cause a large magnetizing current to flow, which can damage our windings. So what we want to have is, we want to have the we want to change the speed of the motor, but keeping the flux constant. What we want to do is, one approach of doing that is V by F control. You will learn, some of you are in the electrical, you will be learning about this V by F control. By changing the V and F in the same proportions, we will be able to have the constant flux, and the torque will be dependent only on the current, how much will be directly proportional to the current. It's a directly proportionality to the torque. So by changing this voltage and frequency, we are able to have the different speeds at the with the same flux. So how can we achieve this variable, to have this variable voltage and frequency? We want to achieve that. which is not possible like uh, with uh, with the like a transformer or something. We are not able to, we can change only the voltage levels but not to the frequency and all, or whatever supply that is coming to any industries or our homes is a of constant voltage. Like how we want to have that variable voltage and variable frequency. Coming to that is like this variable frequency drive, how does it work? Like let us say we are having a three-phase AC supply of like 415 volts with a peak of like around 586. So what is first done is like what we will do is we convert this AC to DC first, like which is being converted by here. The simple is like uncontrolled rectification. What we do is like a three-phase rectifier we have used. So we are able to have this constant DC here, and this capacitor is to filter out any ripple in this voltage. So when we are able to get this DC voltage, now what is our motive is to have a variable. Now we want, from this DC we want to have an AC with the variable amplitude and frequency. As earlier I told you, like we can switch these switches as per our, these are like IGBTs, we can switch as per our need or as per our want, what we want to achieve. We can switch them in such a way, or we can use a certain modulation technique. We can change the amplitude as well as the frequency of the voltage waveform that we can get. Like we can have the voltage waveform with the varying frequency, let us say from 10 to 60 hertz, or let us say 70 hertz. And still also by changing the modulation index as well, which we learn in subsequent classes how it is done in like PWM inverters, like we can change the amplitude of this voltage waveform as well, like by properly adjusting this amplitude as well as the frequency. We can change the speed and torques of these motors, as such like AC motor speed and torque by varying like motor input frequency and the voltage we are able to have. Like option B is the correct answer. Coming to the next question, which of the following just a minute.
Sir, can I have it? Sir?
Hello, yes.
Sir, sir, what kind of harmonics are being generated with this VFD, sir? Harmonic contents are being generated.
Like this will be dependent on the modulation, as well as this will, like it is difficult to make everyone understand what kind of a harmonic to get into the detail of it. But it will certainly depend upon the operation, how you are operating this inverter part, like that is being like this the voltage that is being applied to this AC motor. There are certain modulation techniques which can have a better THD, and like we can use a space vector modulation, we can use a PWM modulation, and that will you subsequently learn further in this course.
Okay, sir, thank you.
Like this is like on a harmonics, like one lecture can be given on this only harmonics, or how we can treat them and how they are generated and all. And then we have to do all the calculations on the voltage waveforms, and to see which of the harmonic components we are having doing the Fourier analysis and all, which will be subsequently, which will be a little early at this moment of this course, and gradually as we go further in this course we can see regarding these harmonics and all when we'll be studying like about inverters and all.
Okay, sir. Thank you.
Okay. There is question number 6 is like which of the following has bipolar voltage withstanding capability? Can someone like which answer?
ACR and G2 bulb.
Can you mute your please and like text? Everyone is saying like 6. Let us go into it. Let us see how an SCR looks like and how a GTO looks like. As you can see, first we'll be discussing about the SCR. Like SCR will be having the three, will be having like anode, cathode, and where A is anode, K is cathode, and G is gate. As you can see, like we are having a PNP configuration here, PNP configuration, and due to this configuration, like and with this gate, there is like gate is connected to the N terminal, and with this configuration you can see like three junctions are being formed like J1, J2, and J3. Let us now understand how it blocks this. Just a minute. Let us now understand when the positive voltage is when the positive voltage is applied across this SCR. When the positive voltage is applied, like J1 is forward biased, J2 is reversed biased, and like J3 is reversed biased. This like forward biased. As you can see, like J1 and J3 are forward biased and J2 is reverse biased, because like this N substrate is close to this positive terminal and it's like negative here. Since like J2 is negative reversely biased, it won't allow any conduction till we give a certain gate that will cause the depletion of this the barrier that will be formed across the junction J2. Similarly, if you can see to the GTO, it has some kind of a similar structure where we are having like a three junctions are being formed, and when we apply a positive voltage across the GTO, J1 and J3 will get forward biased and J2 will get reverse biased. As soon as like we haven't applied, as long as we haven't applied the gate to this GTO, J2 remains in a reverse biased, J2 reverse bias, and it does not allow any current to flow through it. However, when we apply a certain amount of a gate, we give a gate to it like this, J2 junction starts to deplete and it will conduct this positive current. That means like it can block the positive voltage till like some gate isn't given. Now we want to see like what will happen if the negative voltage is given to both SCR and GTO. Now let us give like a negative bias to this SCR and GTO. That means like cathode is positive and anode is negative. Here you can see like J3 and J1 are reverse biased and J2 is forward biased. This means like because of like J1 and J3 being reverse biased, it doesn't allow like negative current to flow through the SCR. That means it is able to. Is my voice clearly audible to everyone else? Like Bharati is texting me like I am not. She's not able to properly hear me. Like my voice isn't clear to her. Like Bharati, there might be some issue with your device, because to everyone else it seems like my voice is clear. So it is so the negative current doesn't flow, so it is able to block the negative voltage as well. Similarly, we can see in the GTO, when the when the reverse bias is applied across it, we can see that J1 and J3 are reverse biased and J2 being forward biased. uh, Still, due to this reverse bias of J1 and J3 junction, like, it is able to block the negative voltage and is not able to it doesn't allow like the negative current to flow through it. As you can see, at any point of time, like if we apply positive voltage, positive biasing or negative biasing, that some junction is getting reverse biased. Due to that, like, it is able to block both polarity of voltage, any polarity of the voltages. So we can see like SCR and GTO both are able to block, have the like both bipolar voltage withstand capability. Coming to the question number 7, what is the relation between breakdown voltage and drift region of a power diode? Anyone can anyone? Like, so coming to this power diode, as we have already seen, like for the power diode we are having like a PN junction with the drift region between which is a very lightly doped region, and we had already discussed, and with this light doping, we are able to withstand high amount of the voltage. But the drawback of this, like with this light doping, as already discussed during this introduction, like due to this lightly doping, the resistivity of this the resistivity increases, like the resistance, on state resistance increases. As you can see, like when the reverse biasing is applied, like uh, the all the voltage, like you can see, when there is a reverse bias, negative and positive, also the barrier potential is formed between this drift region, and it will depend, and the width of this barrier will depend upon the width of this drift region. More the drift region, more will be its width. That means more the drift region, more will be the voltage withstanding capability of this diode. As such, we can say like this, with this drift region is having is a direct function. The relation between this breakdown voltage and the drift region of a power diode have like a direct are directly proportional with each other. With the increase in the drift region, the barrier increases, which in turn increases the breakdown voltage of this power diode. However, the downside of this is like with this thing, the on-state resistance of these diode will increase. Coming to the problem 8, like fast recovery diodes are used in application, and reverse recovery time of these diodes is. Anyone? Anyone? So let us see. First, we will see where fast recovery diodes. Where do we want to use the fast recovery diodes? Fast recovery diodes, like previously discussed, diode turn-off process. to like eliminate this minority carriers in the PN junction. There is we need to have this reverse recovery current, which will cause these which will cause these minority charge carriers to recombine, and then only the current will come to zero. More the this recovery time, more the recovery time, that switch cannot be used for high frequency operation, because still if we want to operate switch the frequency at very high rate, there will be some amount of current that will be flowing at that moment of time, and there will be some amount of current flowing at that of time, which will cause losses in the system. And where do you when there is a fast recovery diode, that means like this recombination is happening in a very small, that's this reverse recovery is happening in very small amount of time. That means like the recombination of these minority carriers is happening in a fraction of a time, like in some microseconds or somewhere in nanoseconds. As such, like these devices can be used for very high frequency operations, because like the current has already been turned off to zero, and we can we can switch on the other device, and we can have the like minimal losses in that case as well. So there is like for application will be high frequency application, and the reverse recovery time of these diodes will be very small. Question number 9. The reverse blocking capability of Schottky diode compared to the power diode is. I think everybody should be able to answer this. Like I think I have discussed this earlier as well while explaining this power diode and Schottky diode. Anyone? So coming to this, like I told you, in the power in this power PN junction power diode, we are having a P type, N type, and we are having a drift region which is lightly doped, and the size of this drift region will be having like different size of the depletion region that will be formed due to this. And since as we can see, because of this we these power diodes are can be used can block very high amount of the voltage. As such, like we can find like these PN junction power diodes up to like kilovolts of range, like 6 kVs or something more than that up to 6 kV. I will be in certain kilovolts. However, in the Schottky diode, we have like metal is directly in contact with this N-type substrate. Like, and the depletion region that is being formed between this metal and the L is very small. As such, like since this depletion region being very small, this diode, this Schottky diode is not able to withstand very high amount of the voltage. And because of these like these metals and the depletion region being very small, we have a very like very low, we can say like in the diode, if like a forward blocking voltage is 0.7, we see like this due to this depletion region being smaller in the Schottky diodes, like this forward voltage drop is also lower in case of the Schottky diodes, around like 0.3 volts or something. And because of these smaller depletion regions, like in during the reverse bias, these have like a lower blocking voltage capabilities. As such, like these Short key diodes can be found of voltage rating about like hundreds of volts, something like that, in the range of hundreds of volts. So the option C is correct. Now coming to the last question: which of the following device has controlled turn on and uncontrolled turn off characteristics? A. SCR, B. diode, C. IGBT, D. MOSFET, and triac. Anyone? Let us like, there are multiple answers that people are giving multiple answers. Let us see like these devices. A brief, you go have already discussed them, but I'll briefly go through them. Like for the diode, we have a uncontrolled turn on as well as an uncontrolled turn off. It will start conducting when a positive when the diode is forward biased, and it will stop conducting if there is a negative current or the reverse bias across the diode. As for the SCR is able to block the forward voltage up to the point when we start giving gate to it. When we apply the gate, like it has a we can it has a controlled turn on, like using the gate current. However, the turn of this SCR is still uncontrolled. Coming to the triac, we had seen like we are having like two SCRs that are connected in anti-parallel fashion, which can conduct the current in both directions. However, we had only the controlled turn on. We didn't have the controlled turn off of the triac. The other option is the MOSFET. So for the MOSFET, like it is the control turn on, and MOSFET and IGBTs both are control turn on and turn off devices. Here, like these switches can these MOSFETs and IGBTs can be turned on by applying a positive gate voltage across the gate and source. And as soon as like we remove the gate or apply the negative gate across the MOSFET and IGBTs stop conducting. As such, we can say like these MOSFETs and IGBT are like control turn on and turn off devices. So like if seeing these options, like triac was also an option in the D, but there was a MOSFET as well, which is both controlled as well as uncontrolled, which is it's a both controlled as well as uncontrolled, which is a both controlled on and off. And like triac has only controlled on. So like this option was half correct. So the only option that was correct is SCR. So these were the questions like that had to be discussed uh, in this week. Like in the every slot, like these are the questions that were discussed like yesterday as well. On Monday, one slot is like between 6 to 8, and today also there is one slot from 6 to 8, and other slot is mine from like 7 to 9. And all of the content remains same for every like for every meeting, because like there are a lot of students enrolled in this course, around like 6,000 students, and some might have like availability on a particular time slot, and they may be able to join in that particular time slot. And yeah, this, and in the subsequent week, like if the assignment deadline is finished, we can discuss the assignments as well, or maybe some other questions pertaining to the topics that will be discussed in this week, in the coming week. And firstly, like I'll be summarizing, have a like today I'll be summarizing this what will be happening, and you are free to ask any questions. And still, if anyone has any questions, like feel free to ask. Yeah, questions in both, in every session. I would say, like, there are three sessions that are happening. One session is on Monday from 6 to 8 p.m. Like, other session is Tuesday on 6 to 8, and one is this 7 to 9. Like, the questions content is same as of now. Like, we will subsequently see what will be the response. If there are only the certain people that are attending and they are available on all the days, maybe we might um, have the different contents on different sessions, but as of now the content is same in every session. I don't know about that 6 to 8 link. I think the link was there, and there was other PhD scholar and who was taking up these problems in that session. And there is always, like, if you are available in some other session, you can join in that, because the content is same. There is the similar thing is being taught there as well as here. Like, about the recorded link, this link will be uploaded on the YouTube, and as well as will be shared with the NPTEL team, and they will intimidate you accordingly, and they'll be sharing this link with you as well, as long along with this presentation as well. This whole content will be shared with you. That YouTube, this is like recording. This session is being recorded, and this session will be uploaded on the YouTube, and you will be getting this YouTube link of the uploaded video from the NPTEL team. No, I don't think tomorrow is any session. I think the next session will be on Monday from 6 to. I'm telling about this live interaction session. I don't know about any other session. There are only three sessions. One is on Monday 6 to 8, and the other is on, there are two sessions on Tuesday and one session on the Monday. Any other question? If there is not any other question, then I think we can conclude this session. Then how will be question? I'm not able to understand what is your question. Then how will be your question, matlab? You can, like, turn on your mic and ask. Thanks a lot. Like, Pavitra or someone was asking the question. She can turn on her mic, and if she wants to ask a question. And if there is if there isn't any other question, I think then we can conclude this meeting. Okay. Good night, everyone. Sir, I'm asking about the exam. How will be the questions? Okay. Regarding the exams, I don't know about the pattern, how the exam will be conducted. I think about the pattern and the questions, you will be intimidated before. What will be the pattern and what kind of the questions will be there. Maybe if someone has enrolled already in some other course, and they might be knowing what the pattern is on the NPTEL and all, then I think uh, they can help you with. As of now, like, I don't know about the examination pattern. That is up to the professor who is teaching this course and NPTEL team. The mode, like, they will be taking this exam and all. Okay, any other questions? Okay, thank you. Good night.